Bienvenidos a todos, bienvenidos a los seminarios internacionales de fronteras de la ciencia de materiales. Hoy es un gusto tener con nosotros a David Morris, que viene del Departamento de Metalurgia Física del Centro Nacional de Investigaciones Metalúrgicas, parte de la entidad española de investigación por excelencia, que es el CSIC, y nos va a dar una breve historia, no sé muy bien cómo traducirlo, de los intermetálicos estructurales modernos. David tiene un largo bagaje investigador, empezó allí por los años 70 realizando su tesis doctoral en la Universidad de Birmingham, en el Reino Unido. Luego del 74 al 77 fue científico e investigador en el laboratorio de energía atómica en Harwell, y del 77 al 85 estuvo en Lausanne, en el Instituto CERAC, como investigador también. Posteriormente, desde el 85 hasta el 88, pasó a la Universidad de Neuchâtel, fue profesor de ciencia de materiales allí en Suiza, y entre el 98 y 2000 nos hizo una visita como profesor en año sabático en el Centro Nacional de Investigaciones Metalúrgicas, y a raíz de esto pues se quedó vinculado a España, y desde el año 2000 pues es profesor de investigación en el CENIM, y desde entonces nos acompaña. Hoy viene a hablarnos de sus líneas de investigación y trabajo, que están principalmente centradas en aleaciones de cobre, intermetálicos, en materiales nanoestructurados, metaestables, en aleación mecánica y en solidificación rápida. Es realmente un placer tenerle hoy con nosotros, y bueno, me han hablado de charlas parecidas a esta y me han hablado extraordinariamente bien, o sea que espero que todos la disfrutéis tanto como la estoy esperando yo. Así que muy bienvenido, muchas gracias por estar aquí, David.
Vale, muchas gracias.
El tiempo es tuyo.
Vale, muy bien. Potted, English first of all. Potted means a little bit what you put in the jar of marmalade. You take the chunks and you throw them in, and sort of everybody's contained within that environment. What I want to do today is to go back over the last 50 years, but especially over the last 20 or 30 years, and discuss what's happened with intermetallics. Intermetallics has been one of, I would say, the most interesting scientific and productive areas over the last 20, 30 years. What I'd like to do is to start off with a brief description of what do we mean by intermetallics, what are typical properties, why do they have these properties, and then look at a couple of intermetallics which are really very close or into applications as structural materials. There are many intermetallics used for their physical properties, superconductivity, conductivity, etc. I'm not going to talk about those here today. What are intermetallics? Now, you all know about these gamma-gamma prime superalloys. In a gamma-gamma prime superalloy, you've got basically a nickel matrix, an FCC metal, and inside you've got a very high volume fraction of these precipitates called Ni3Al. So looking at the phase diagram, a mixture of the gamma FCC matrix with Ni3Al. Now, what we're going to be talking about today is taking the material of the precipitates, and that's going to be our bulk material. Now, when we mix two elements A and B, a number of things can happen, and it all depends on whether you want or not to form AB bonds. So if I mix atom A and atom B, and they really don't care whether they are next door neighbors or not, you'll get a disordered solution, and that's what you've got in most conventional metallic materials, in aluminium alloys, in steels, for example. If you don't want to form AB bonds, you prefer to have AA and BB, then you'll have some sort of phase decomposition into an A phase, a black phase, and a white phase. Whereas if you do want to form AB bonds, the way to do it is to order the atoms, and the reason for the ordering can be size or electrical or electronic. A large atom wants to have a small atom as a neighbor so they can fit together spatially. So if we want to form AB bonds, we're going to get an ordered structure. Now, a couple of words of definitions. Intermetallic compounds strictly are those which remain ordered up to the melting point. They're strongly ordered and they don't want a disorder in the crystalline state. Ordered alloys are alloys which at low temperature are atomically ordered, then they disorder, and only somewhat later, at a much higher temperature, will they actually melt. A second definition, Daltonides. Many of the intermetallic compounds were discovered by the chemists in the 18th century when they were mixing metals together and finding strange properties at strange compositions. And so Dalton is one of these famous chemists, and he found, or these people found, that at certain strict chemical compositions you would have a sort of chemical reaction and you form a compound with a well-defined chemistry, A3B2 and so on. There are many others which are called Bertholite compounds, where you can have a wide range of chemical compositions and still maintain the ordered structure. Now today we're going to mix all these together and call these intermetallic compounds. And if we look at a couple of examples of phase diagrams, this is the nickel-aluminium phase diagram again. Here's the nickel end, solid solution nickel. Here's the Ni3Al intermetallic. You see it exists over a fairly narrow composition range and is ordered all the way up to melting. Here's another compound, the NiAl. It's got a different chemical structure, a different phase. It's ordered over a fairly wide composition range, again all the way up to the melting point. It's very strongly ordered. If we contrast with the iron aluminide, here's iron aluminium. Here we've got the FeAl phase region, ordered up to about melting over a wide composition range, very much the same as NiAl. But in this case, at Fe3Al, we've got another phase which exists over a moderately wide composition range, ordered only up to about 550 centigrade. Then it disorders. And in the moly-silicon phase diagram, here we've got a couple of intermetallic compounds which are Daltonides. The chemical composition is very well defined, and they're very strong intermetallics, ordered all the way up to the melting point. Okay, now let's look a little bit further. Let's look at the electronic structure. Inside, and what we're going to say is that the intermetallic is sort of halfway between the metal alloy, the disordered metal alloy, and the ceramic. Now inside a typical metallic alloy, you're going to have a positive ion, the nucleus, with electrons in circular or spherical symmetry around it, and then you've got a cloud of electrons that are free to move, that give you conductivity. Inside the intermetallic, here we've got the ion in the center in the same way. We've got a cloud of electrons. These are still metallic alloys. They conduct heat and electricity. But what you see is that we're no longer circularly spherical symmetry. We've got a stiffening of the bonds and a directionality of the bonds. So we are, as you see, in between metallic, non-directional, rather weak bonding, and ceramic, ionic or covalent, strong directional bonding. We're sort of halfway in between. Now if we look at the crystal structure, here's the BCC crystal structure, which you would find of iron, of steel. In that case, each atom would have the same identity. And this vector from the corner to the center, it's the half 1, 1, 1, is the easiest vector of shifting. That's the vector of the dislocation that carries out deformation. Now in the ordered cell, we've got iron on the corners, aluminium in the center. A half 1, 1, 1 vector takes a black atom to a white site. It disorders. And the crystal doesn't like that. It likes to stay ordered. We've got two alternatives. We can double up. Instead of having a half 1, 1, 1, we have a full 1, 1, 1 vector. Or we can go to a 1, 0, 0 vector. In both cases, they're larger vectors. Energy of dislocation goes with B squared. So they're much more energetic. They're more difficult to produce. And what we've seen is that here's an AB ordered matrix. Here's the one dislocation, and ABAA. This is the disorder behind it. What do? I couple the one dislocation with a second one that repairs the order. And this is the super dislocation. Now there are various types depending on the precise crystal structure and what sort of stacking fault. It's very much the equivalent of two Shockley partials with a stacking fault in between. The type of dislocation I get depends on the precise crystal structure, but in all cases the core of the dislocation, or the dislocation, is now not a point object, it's a planar object. You can think of it as a ribbon in three-dimensional space, which means it's more difficult to change plane. Things like cross-slip, moving a dislocation over an obstacle is more difficult. Now if I look at the core of the dislocation, and this is a little bit esoteric, but I've put here in red, is probably the most important characteristic of these dislocations in intermetallics, or if you like in ceramics as well. Here's a super dislocation made up of two cores with a stacking fault in between. And the cores plus that plane, the stacking fault, defines this is the plane of easy movement of the dislocation. The core itself is not a point object, it elastically relaxes. This dimension is something like 1 nanometer. The core relaxes over something like a nanometer, and because the elastic properties are anisotropic, directional, stronger in some directions than in others, the core spreads out in the elastically most floppy, the weakest direction. So the core looks like that, and here it looks like that. So the dislocation is now this three-dimensional object. There's no easy plane. I need thermal activation as well as a lot of stress to move it. So creating the dislocation is more difficult because of the larger Burgers vector, and moving it, because of this core, this is the pile stress, moving it is more difficult. Now if creating and moving is difficult, the good news is that I've got a stronger material. Now the bad news is that I may have got, as a ceramic, in the ceramic the core makes it difficult to move a dislocation. As in the ceramic I may become brittle because of cleavage cracking. Now in the ideal case, a cleavage crack is atomically sharp, and we're going to break bonds one by one by one by one as this cleavage crack propagates forward. So it's very brittle. That's what silicon is, that's what iron is. That's what intermetallics tend to be. So here we've got some ab initio modeling showing what may happen at the crack tip. If we want to go from really brittle to being somewhat or more and more ductile, what we need to do from the crack tip is nucleate and shoot away, throw away a dislocation. Now if we can throw away a dislocation, we blunt the crack tip, becomes more difficult to propagate further, we've increased the toughness, and eventually we become ductile. Now the Burgers vector was twice as high, something like that, so the energy is 4 times as high. Moving it away is difficult, and because it's difficult to nucleate and throw away, there's a risk of, with high strength, low ductility. What else does order do for us? When we talk about an atomic process like diffusion, what we're talking about is swapping a vacancy with the next door neighbor. Now if I have a vacancy in an ordered lattice AB, 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 if I have a vacancy here and I want to move the B atom, swap it with a vacancy, I'm going to move the atom onto an A site. The crystal doesn't want to do that, so anything that depends on atomic movement is slowed down. Diffusion is slowed down. Here's an example of creep under conditions where the creep rate depends on the diffusivity. So this is creep rate as a function of reciprocal temperature. At low temperature, we're highly ordered and diffusion is slow. When I reach a temperature with this alloy disorders, then suddenly the diffusivity, and so the creep rate, increases by 2 or 3 orders of magnitude. Anything that depends on atomic movement will be delayed inside the ordered state. And again, if I'm looking at a high temperature application, lowering diffusivity as well as making dislocation nucleation difficult is good news. So summarizing, and it comes from the strong bonding and the difficulty of dislocation nucleation motion. We're elastically stiffer. We've got higher strength. For the two reasons, it's a larger dislocation structure and the pile stress. High temperature strength, if we can pin dislocations, low diffusivity. Low density, what I've not said so far is that what we're always doing is mixing, in the structural applications at least, we're mixing a transition metal with a light metal, especially aluminium or silicon. So if I mix a lot of nickel or iron with aluminium or silicon, I've got a much lower density alloy. And again, I've not talked about it so far, since we have a lot of aluminium or silicon, we're going to form a naturally protecting alumina or silicon scale. So a couple of maps that show then typical changes of properties because of these elastic and structural reasons. The strength and the density. Now here we've got steel, typical strength, typical density. Here's iron aluminide. I've put in a lot of aluminium. The density has come down a lot. The strength has not changed very much, actually. Nickel alloys and NiAl. Titanium alloys and TiAl. In very general terms, the strength has not changed very much here, but the density, yes, has reduced. Toughness and Young's modulus. Here's steel. The steel's range of toughness, typical density, sorry, we're here on Young's modulus, typical modulus around 200 GPa. Here's the iron aluminide. Toughness has come down somewhat, depending on which aluminide you're looking at, and stiffness has gone up. Titanium alloys and TiAl. We're always increasing modulus and lowering toughness. So, the good news is that we have the possibility of increasing strength and oxidation and stiffness and so on. The bad news is watch out, especially for ductility, and also creep resistance is sometimes not too good. This has been the big problem over the last, let me say, about 20 years. And really solutions have been found by macro and micro alloying, changing, adjusting the chemical composition, and by adjusting the mixture of phases, as well as going to careful processing. Okay, why are we interested? Here's a statement that was made by the Advisory Council for Aeronautics Research, now about 15 years ago in Europe. There's a big problem of, this statement was made in the context of aero engines. We're worried about CO2, we're worried about these other pollutants. We need to do something, we need to do a lot in terms of energy efficiency. And you can go a long way through engineering, but if you want to achieve this sort of improvement, you've got to go to new materials. There's absolutely no question of doubt. Now, what are the materials that we're using for high temperature structural applications? Specific strength is typically more important. If you're rotating a turbine, it's the density that plays a role as well as the speed at which you're turning. If you're flying, again, weight is important. So specific strength we're looking at here, strength divided by density, and depending on the operating temperature. This is where the titanium alloys are found here at the high temperature single crystal superalloys. Here's what TiAl could be compared with titanium alloys. Here we've got steels, and here we've got iron aluminides on top. So what I'd like to do now in the remaining time is to look at a couple of important intermetallics, see why are they important, what's been done to their development over the last couple of years, and where are we in terms of applications. First of all, the gamma TiAl, this is a light, stiff, oxidation resisting material, but it's also brittle. There are many dislocation varieties. They're not all terribly mobile because of the pile stress problem. Here's the phase diagram of titanium, aluminium. Here's the TiAl region. It exists over a fairly wide composition range, exists ordered up to the melting point. Now, one important thing is that if we take that alloy, or take the compound, melt it down, we run through a peritectic. A peritectic always means that there's a large composition fluctuation. There's lots of segregation inside the alloy, which is very difficult. Also interest in Ti3Al, which has got a different crystal structure, and most of the research over the last 20 years has looked at alloys in this, what's called the alpha-gamma Ti3Al, TiAl composition range. So not with 25% aluminium, not with 50% aluminium, but somewhere in between where you've got a mixture of the two. Now, of great interest here for these alloys, between 25 and 50% aluminium, you have a eutectoid. Now, those that know about steels know that you have a eutectoid transformation, and what the steels people do is to heat their material up into the high temperature gamma, the austenite phase field, and then cool it down to obtain pearlite or martensite or whatever. The eutectoid temperature offers you the ability of heat treatment for microstructural control and then property control. It's very important. Now, here are the two types of microstructure that you can get simply by heat treating. This is one of these alpha-gamma alloys. Simply by heat treating the final object after machining, after forming, after everything you want, we heat it up to high temperature, cool it down relatively quickly, or cool it down rather slowly. Here what we've got are grains, something like 25 microns in size. Within them there's a lamellar structure. It's exactly the equivalent of pearlite in steels. Or if I cool very slowly, here I've got globular grains of gamma with, at the grain boundaries, large chunks of alpha-2. And it's very easy to heat up the material and heat again if I want to, heat up the material, cool down in the controlled manner to achieve this structure and these properties, or this and this. Now, what's happened to the, this is maybe 1990 to 2010. There have been changes of processing technique and changes of alloy composition. Titanium plus aluminium is very, very reactive when you heat it up towards the melting point. It reacts with the crucible, if you're trying to melt it, it reacts with the environment. So there's been lots of development of plasma, cold hearth, under vacuum. There's been the development of techniques, very much as you have for titanium alloys, but going a little bit further. And in terms of chemical composition, the balance of alpha against titanium tells us how much of the Ti3Al, the alpha, and how much of TiAl, the gamma phase, we'll have in the mixture. And then adding chromium manganese especially, we improve ductility. Adding things like niobium, tantalum, molybdenum, we improve oxidation resistance because we want to use these at as high a temperature as possible. And then adding often interstitial elements, we improve the creep strength. So over the decades, there have been a number of phases or stages of research development. The very first phase said, let's have a look at TiAl, single phase. It's very brittle, even though it's got some properties, very brittle. So we jumped very quickly to this alpha-2, alpha Ti3Al plus gamma TiAl mixture. And as in a composite, we get ductility from the one phase, we get strength from the other, and we mix the proportion of the two according to how much ductility, how much strength, how much toughness do we want. Then we need to improve creep and oxidation, so we add these BCC metals. Then there's this problem of the peritectic solidification. It means that the composition changes greatly within the one alloy. And that will affect, in one part of the alloy, the same component, you may be here, in another part you may be there. That's not allowed. And so adjusting the composition by careful adjustment of these, avoiding the peritectic solidification and avoiding the segregation problems that go with it. And then this lamellar structure is very often the structure that we want. It decomposes during a long time at high temperature, so the properties change, and so we have to do something about that. The creep problem has been a great problem after having developed alloys and structures that had suitable strength and toughness and so on. For the reason that we see here we're looking at the creep rate as a function of time or strain. We're creeping at 700 Celsius. Let's add a stress of something like 300, 350 megapascals. What we see is that the creep rate is enormously high for something like 1% strain, and then the material work hardens and the creep rate becomes acceptably low. But of course, if you think of a turbine blade that's spinning inside a container, what we cannot do is to allow this component to stretch 1%. It's too much. And so avoiding this primary creep strain has been a great problem. The reason it happens is that within a given phase, it's very easy to emit twin dislocations or emit normal dislocations. And it's only when these interact that you have a sort of work hardening that the creep rate becomes very, very low. Until then, it's a very soft grain. It's a very soft material. Okay, so where are we today? By the selection of alloy composition, by the selection of type of phase and mixture of phase, we can balance properties. If we want high fracture toughness, we go to the lamellar structure. If we want ductility, we go to the opposing, the duplex, the globular structure. If we want strength, lamellar and solution hardening. If we want creep strength, fine lamellae and precipitates. If we want oxidation, so today we essentially know within limits how to adjust. And what's the status? The status is that we're into applications. Now here's a jet engine. This is supposed to be the GE90 engine. Here you've got the various fan blades at the front where drawing in cold air, compressing it. Here we're burning it. And then out comes the hot gas. Here we've got the superalloys. And here at the very back in 1-2 stages, today we've got per stage something like 100 of these low pressure turbine blades of one of the alloys. There's something like 20,000 of these blades flying. And they're flying inside the GE90 engine. Next time you go on a 787 or the upgraded 747, look and see if you've got a GE90, and if you have, you're flying titanium aluminide. So that's a good success story. Now, in the same way, these valves were used in Formula One racing engines from about the year 2000 to the year 2005, and then they were banned. And they were banned because, now, clearly in this case, you're rotating a component as fast as you can. Here, you've got something oscillating and closing. So if you can make this of a low density material, you've got an engine that is more efficient. It was so efficient that it was banned. It gave too much of an advantage to, I mean, as has happened this year with Formula One, you can't make these engines too efficient. Okay, what does the turbine blade want? It wants a balance of properties. It's a balance of properties with balanced composition, with balanced microstructure. You need high cycle fatigue, strength at high temperature especially. Low cycle fatigue at high temperature. Room temperature is also important because you've got to sort of switch the turbine on at some stage. Creep you need, ductility you need, and this has been a very great, I would say, success story of education of the design engineer. The design engineer of these things, of these sort of turbines, turbine blades, is using very exotic material, but is often a very conservative person that has been used over his lifetime to working with superalloys probably that have, I don't know, 5% ductility. And when he was told work with 2% ductility, impossible. Now he's working with 1% ductility. And that's been a very great educational story, convincing the engineer that 1% ductility is all you need. The turbine blade drops on the floor, you bang it gently with a hammer when nobody's looking and put it in. And that's where you need 1% ductility. Domestic object damage. This means if a bird flies in the front end, you don't want to spit out too many broken blades at the back end. And when we look at then these exhaust valves in the engine, very much the same properties, high temperature, high cycle fatigue, oxidation resistance, wear, etc. Okay, let me jump to another family, the second family I want to look at, the silicides. This is the molybdenum silicon phase diagram, and we've seen before we have a couple of these Daltonide compounds, very strongly ordered intermetallics. Pile stresses are so high, dislocations are not going to move. Don't bother about the word ductility. You need to use the toughness concept as you do for ceramics. They don't deform plastically, but they are metallic, so they've got high thermal and electrical conductivity. High thermal means that you can cool them actively, which is a significant gain over the ceramic. Electrical means that they can be electrical discharge machined, as you cannot with ceramics. They're castable, they are metallic alloys. You can mix them up in the liquid state and cast them to shape. Oxidation resistance, very good. And we're moving further than TiAl towards ceramics. Now, what's the interest? The great big success story of gamma prime nickel-based superalloys, perhaps of the cobalt superalloys as well, has been a tremendous success in the hot zone of the jet engine. And these alloys have an upper limit of operation temperature of 1,000 degrees and a little bit more. And what the turbine makers are hoping for with molybdenum silicides, or perhaps with niobium silicides, this may be a little bit more British with Rolls-Royce, this may be a little bit more American with GE, with these silicides to jump up to significantly higher temperatures, temperatures where superalloys have, if not yet molten, they've become extremely soft. So again, you also know this story, the temperature, the upper temperature limit of usage of superalloy over the years, over the decades, evolution of composition, evolution of processing, cast, wrought, directionally solidified single crystals. But what is clear is that superalloys are not going to go very much more in terms of gain of temperature, whereas just around the corner, we're almost there, supposedly, are these silicides. So why the moly-silicide boron specifically? Here's molybdenum, single phase, a very bad oxidation resistance. That's why we don't find molybdenum used very much as a structural material. Here's MO3Si, here's MO5SiB2, both very strong phases at high temperature, both wonderfully oxidation resistant. And by looking at alloys with this sort of composition, we'll have a three-phase mixture of this, which will give us toughness. The more molybdenum we have, the higher the toughness. The more of these intermetallics, the more oxidation resistance. And so the game here is to balance these equilibrium phases, have a balance such that we get a balance of properties. Now here are two microstructures. I think they're both cast materials, one with about 40% of the molybdenum phase, one with about 50%. Toughness is something like 8, perhaps 10 megapascal root meter. For those of you that work with ceramics, it's pretty much ceramic, maybe a little bit better. But of course it's castable, it's machinable, it's coolable. And here we can do a tensile test at 1200 C with a yield stress of above 300 megapascals. The problems you have with measuring this is that all the dyes, all the testing devices have softened before you actually measure these materials. Okay, let me jump to the third family that I want to talk about, the iron aluminides, iron aluminium. Here's the FeAl phase region, ordered all the way up to the melting point. Here's the Fe3Al phase region, ordered up to about 550 Celsius. Now, we've got steel with a lot of aluminium, so it's a very low density steel. These will be, they form a natural alumina that protects. So you don't need lots of chromium or lots of nickel to get the properties. They're very cheap in terms of basic alloying additions. We've got order strengthening, and we've got a high specific modulus. The modulus is a little bit higher than steel, and the density is much lower. Now, a summary of the properties. Here what we have is strength as a function of aluminium content. We're going from basically steel down here, which will be soft. As we add in aluminium up to Fe3Al, so the strength increases dramatically. As I move from Fe3Al to FeAl, the strength comes down somewhat from this maximum, but is still respectively strong. Now, unfortunately, if I look at ductility as a function of aluminium content, I've really got the reciprocal. Iron, or iron with a small amount of aluminium, is ductile, tough. When we reach Fe3Al, there's almost no ductility, very poor toughness. But as I come back towards FeAl, so the ductility comes back somewhat. And the reason for all of this, of course, is that we've made it difficult to nucleate the dislocation, difficult to move it away because of the pile stresses. And so the crack tip doesn't blunt. What do we need to do? As a metallurgist, we need to refine the microstructure. Here, each of these lines defines the ductility, strength, envelope for material of a given grain size. If I go from something like 100 micron grain size to 10 micron down to 1 micron, I push the envelope up diagonally to higher ductility strength for the same ductility. Just to show you a couple of dislocations we've been talking about. This is iron with aluminium in disordered solid solution. It's a small amount of aluminium. And what we've got is a disordered lattice, very much like iron itself. So here we're looking in bright field and in dark field. Here what we see are the single dislocations exactly as in steel, and perhaps the beginning of a dipole wall structure with some dipoles, some debris in the background, exactly as if we were deforming pure iron. When I move to Fe3Al, now what we've got are pairs of dislocations. I hope you can see the pairs here. The front one destroys order, so we pair a second one to repair the order. Here we're looking at the dislocations, and here in different contrast we're looking at the stacking fault, the antiphase boundary. Now if I go into the FeAl region, higher aluminium than Fe3Al, again I've got paired dislocations. I hope you can see these pairs, they're super dislocations. But of great interest is that these can react together and can decompose. They're very complicated dislocations. And here I've got something like a Burgers 1 dislocation and a Burgers 2 dislocation reacting to produce a Burgers 3. And that is a little node that cannot be moved in any direction. So it's an additional type of obstacle. Or here's a dislocation which, where it's bent over, is starting to decompose into two partials. And again, the partials don't want to move, so this is a pinning point. Now these sorts of pinning points give rise to what is a very strange behavior known as the stress anomaly that you find in very many of the intermetallics. And it occurs because the dislocations are complicated. At low temperature they glide as much as they can, but at high temperature they react together, form nodes that are obstacles, or decompose to become unmovable objects. So what we have is the anomalous strengthening, which is very strange, that's why it's called anomalous, we have here a material, if I test it at room temperature, will have a strength of 100, 150 megapascals. If I test it at 600 Celsius, has a strength of 300 megapascals. It's a wonderfully strange thing, a material that is much stronger at high temperature than at low temperature. Now, unfortunately, when we look at creep strength, and what I'm saying here applies exactly to all steels. The iron aluminides are ferritic steels with a lot of aluminium. At temperatures below, what we're looking at here is the stress that we can apply for a creep life of 1,000 hours as a function of temperature. If I apply a high creep stress, that's okay at low temperature, below about 500 Celsius, but when I get to 600, or especially when I get to 700 Celsius, the creep strength has come down enormously. And so what do we do with steels? I do exactly the same with the iron aluminides. I add carbides, I add whatever chromium steels, I add whatever obstacle I can to delay, to slow dislocation movement. And there's a tremendous activity at the moment to try and improve steels that can function in this 600 to 700 temperature range. It's a tremendous problem, and of course the same applies to the iron aluminides. Now, there's been an enormous activity on improving creep resistance of iron aluminides, a lot in Germany, a lot here in Madrid also, and a lot in the Czech Republic. And you see here in this messy graph on the right, this is the creep rate for a given applied stress at 700 Celsius. This is the stress that we can apply for these creep rates in the binary iron aluminide or binary iron aluminide adding chromium. No strengthening particles. If we add titanium that forms particles, or boron, or nickel, or tantalum, or zirconium, all of these form second phase particles of different types that have better and better stability. And so the strength has been improved by 1 order of magnitude over the last about 10 years. Let me say a few words about the oxidation corrosion resistance. Here what we're looking at is the change of weight. If I hold this material, cyclic testing at 800 Celsius. 800 degrees is a very high temperature for a normal chromium steel. Here's iron with 9% chromium. It cannot withstand 800 degrees, and it's oxidizing like mad. It's forming a very thick oxide film. If the film stays stuck on, it still isn't going to protect me. I'm going to consume all the metal. Here's another example of iron 13 chrome with a little bit of yttria, and here it's oxidizing like mad, and the oxide is flaking away because of the thermal shock that we're putting on. These alloys here are all alloys that contain 15 and 20% aluminium. Adding in aluminium means that you oxidize, you form something like a nanometer thick oxide, alumina layer, and then you stop. You protect yourself. Again, oxidation resistance. Here we're looking at the change of weight as a function of aluminium content. We're annealing this material at 600 or 1000 or 1200. Now, you don't hold a steel at 1000 or 1200 degrees and hope that it's going to remain metallic. It's going to oxidize very quickly. And it's what we see. There's been an enormous weight gain. This will mean full oxidation to no metal remaining. When the aluminium content is below something like 12 or maybe 15%, there's this enormous oxidation. The moment you're above 15 or 20% of aluminium, then you form a thin oxide layer which sticks, protects, and that's the end of the story. And this alumina layer applies to oxidizing conditions, but also to carburizing and sulfidizing. And there are very many industrial environments in the petrochemical area, for example, where you've got a carbon excess, you've got a dirty sulfur-containing coal. And all these aluminides are absolutely wonderful. They simply sit there and laugh. So where are we in terms of applications? The picture's a little bit dark here. This is the burner of this coal dust burning power plant in Poland. Here are a couple of humans giving you some idea of the scale. This is the nozzle where the coal dust and maybe air or oxygen is injected. Here's a burner, and inside the burner we've got these blades that are controlling the flow and the direction of flow of the coal dust and the oxygen. And when these were made of high chromium, high nickel refractory steels, their lifetime was very short indeed. Made of iron aluminide, there's absolutely no problem. Here's a second example. This is an industrial filter. We're filtering out, I don't know, carbon particles, maybe oxide particles from within some dirty industrial, very hot gas. Here's a fuel element, which is made of iron aluminide. Again, a couple of humans to give you some idea of the scale. There's something like 100 or so of these fuel elements here in this filter. Catalysis, electrosynthesis of, this is bleach. On tons of bleach are used per ton of paper pulp, wood pulp to make white paper. This is an enormously difficult oxidizing environment. If you make your container out of iron or steel, this is what happens. Make it out of iron aluminide, and this is what happens. And of course, at the present day, in the future, I've been talking about high temperature applications, very often inside a turbine, we're rotating. If it's in an aircraft, we're flying. But whether that turbine is found behind a nuclear power station, whether it's found between this solar heat-powered station, in all cases, what we need for thermodynamic efficiency is to get to as high a temperature as we can manage. Efficiency goes up. So a material, and whether it's a silicide, whether it's an aluminide of titanium, of iron, in all cases what we need is resistance to creep, resistance to fracture, resistance to oxidation, dirty attack in the industrial environment. So with that, let me finish. That's where we are. We're at a stage where essentially research is finished. I mean, the answers are there. We know that you need to have a multi-phase mixture because you have multiple demands for properties. You need oxidation resistance, but also creep and toughness and so on. The world is learning that when it has to, it must accept low limits of ductility, and engineers are beginning to move away a little bit from the dogma of this was what we always thought we needed, to this is what we can actually get away with. We need medium-fine microstructures, of course, depending on whether it's really creep-controlled or ductility-controlled, the application. Often we have a ductile matrix, which is environmentally resistant. With the titanium aluminide, we've got, which we don't with the other intermetallics, we've got this option of high temperature workability and low temperature usability. Structural stability has been a problem, especially when we're looking for creep resistance, but the problems have been essentially sort of solved. You can cast these materials, watch out for segregation. And the story has been one of composition control, but it's really been one of microstructure control. Control the mixture of phases and the size morphology. And the applications are here, and I think over the next decade we're going to see more and more that will be coming. So with that, let me thank you all for your attention.
Thank you very much, David, for so nice talk. And we have time for some questions. I think that can be in English or also in Spanish.
Whichever, yes. Yeah.
No questions?
I have one.
One moment, please. Excuse me.
Yeah, you have to go down.
In order to record.
Actually. Is it on? Yeah.
Yes, yes.
I'm just wondering, once you tune the microstructure to whatever you want it to be, but then you process it, then you manufacture something out of it, then you once again upset the microstructure, so then there is a lot of post-processing that comes into play in all of them. So
yes, in all of them.
What's the degree of post-processing that's required in comparison with other? Is it very large and complex, or does it, you know, it really depends on the application?
It depends on the intermetallic and the application, which says everything but nothing. I think these are alloys that are more sensitive to composition than general alloys. In a general steel, whatever that is, if you change the solid solution a little bit, it doesn't matter. Within plus or minus 10% of the addition, so if you've got 10% addition, it's maybe plus or minus 1%. That will affect the precipitation maybe that you will get. But in the case of the gamma prime, gamma prime is at 25% aluminium, the alpha is at 25, the gamma is at 50, but the phase fields come together, and if you've got 1% composition difference between of aluminium between the one and the other, that's much too much. So this peritectic solidification that left you with dendrites that were maybe 3% off the rest, that's been a great big problem for a long time. When you have segregation in a traditional material, you'll often high temperature forge and recrystallize to try and get lots of atomic movement and homogenize. These are low diffusivity, and forging is difficult. So, so these few percents of chemical composition in homogeneity have been really too much. This beta phase solidification has been a wonderful solution out of it. Specifically, the titanium aluminides are formable, forgeable at high temperature, but difficult, because they're surface reactive, and they are very strong at high temperature and low ductility at high temperature. And so there's been a great movement towards having a cast structure which is chemically rather homogeneous, that can be processed thermally only. So you will try to cast to as near net as you can, and you can forge, you can roll. So there will be the possibility of, by forming, going to near net after the casting. But in all cases, the trend has been, and I think there's been a lot of success in this, to adjusting the composition such that you don't get the peritectic great change of composition, and then subsequent heat treatment is all that's needed, actually. So you'll try to cast to as near a net shape as you can, and if you need thermomechanical forming, it's because you're going further towards near net shape, but not as a necessity from the alloy composition.
Thank you very much.
Any other question? I think that this is a very exciting talk and very exciting future for these new materials.
Yes,
we have learned a lot of them, but I think that for the future we have a lot of new applications and a lot of new challenges.
Yes, yes. So there's still many challenges.
Yes. Yes. Thank you very much. Okay. It has been a pleasure for us to have you here.
Thank you.
And this is your home.
Thank you.